and welcome to this episode of Night Sky News for December 2023 with me, astrophysicist Dr. Becky Smethurst. This is the show where we chat about what you should look out for in the night sky in the next few weeks, and then we chat about what's been happening in space news in the past few weeks. In this episode, we're chatting about one of the highest energy cosmic rays ever detected, plus the discovery of a 6-planet system, which are all in perfect resonance with each other, and we're chatting about where all the exomoons are and much more. There's chapter markers down here if you want to skip ahead to any of those specific news stories, plus any scientific research papers I mentioned are all going to be linked in the video description down below, free to read. So without any further ado, let's kick things off and start by looking up. We have officially reached the longest night of the year here in the Northern Hemisphere with the winter solstice, which this year occurs at 3 a.m. GMT on Friday, the 22nd of December. Now, if you're wondering how, the solstice, which is the winter solstice is, the shortest day and the longest night, can actually occur at a specific time on that day, it's because the solstice is actually defined by the position of the sun in relation to the background stars. You can think of it kind of like longitude, but on the sky. So 0 degrees longitude, is GMT, runs through London. 0 degrees on the sky is where the sun is on the March equinox, when you've got equal day and equal night. And the winter solstice is when the sun is 270 degrees around from that position. What it essentially means, for those of us up in the Northern Hemisphere anyway, is that we have got incredibly long nights that we should take advantage of to stargaze while we can, because the nights are only going to get shorter from here on out. So on the nights of the 21st and 22nd of December, the just past half moon will be close to the planet Jupiter on the sky before they're moving closer to the Pleiades star cluster on the 23rd and 24th as the moon gets closer to becoming a full moon. Pleiades is the one that looks like a little mini Big Dipper or Plough constellation, and it is one of my favorite things to look at in the winter sky. Once you spotted it, your eyes will always find it again. It's just beautiful. Now, the moon will be very bright because it's getting close to full, so it will wash out a lot of the stars that you would otherwise see if you look at Pleiades with binoculars or a telescope. But if you're not sure where to look, it is just a good trick to find things like Pleiades and Jupiter on nights where the moon is there, so that you know where they are in relation to, things in your back garden. You can come back another night when it's much darker and look again, because this part of the sky is incredible during the winter. It just feels like there's so much going on. Plus, by the night of Christmas Day, the almost full moon is going to be smack bang in the middle of the winter hexagon that I talked about last month. 6 of the brightest stars in the winter sky that are a sight not to be missed. Also, if you have clear skies on either Christmas Eve or Christmas Day morning, look out for the International Space Station passing overhead where you live. Because I give this warning every year to parents of kids out there, because the International Space Station can look very convincingly like its Father Christmas's sleigh. It moves very fast and it's incredibly bright. So, I wouldn't want any kids out there to get the two confused. Now, thankfully, NASA have a helpful website that you can look up when the International Space Station will be passing over where you live and which direction to look in. For example, here in Oxford on Christmas Day morning at 6 a.m, the International Space Station will go directly overhead, appearing first in the west and then setting in the east 6 minutes later. So if you are up that early anyway, it might be a good thing for the whole family to look out for in the night sky. While you're there, look to the east for Venus rising in the early morning sky. It's the brightest thing in the sky after the moon, so hopefully you won't be able to miss it as it shines out as a beautiful Christmas morning star. It's not just Christmas morning you can see Venus though, it's visible throughout December and January now, so if you're ever up that early and you've got clear skies, look towards the sunrise in the east and see if you can spot it. Speaking of January, heading into the new year, those of us in the Northern Hemisphere have got yet another meteor shower to look forward to, the Quadrantids meteor shower, which peaks next year on the 4th of January 2024, but you'll start seeing meteors from around about the 28th of December, right through till the 12th of January. So if you're out stargazing on those nights, just keep an eye out for a few shooting stars. Now, in previous years on the peak, the Quadrantids has given us about 200 meteors per hour, so they're known to put on a show, but this year Best estimates put it around about 100 meteors an hour or so. Still a pretty good show, but that's only in the darkest of skies at the peak at 1 a.m. on the morning of the 4th of January. So that number of meteors is going to drop off, depending on how close to light pollution you are. If there's a lot of light pollution, that's going to wash out all but the brightest of meteors, so you will see less of them. And also, what day you're actually going out to look for the meteors, like how far either side from the peak are you? The meteors are all going to appear to be coming from near the handle of the Plough or Big Dipper constellation, hence why this isn't one for anyone in the southern hemisphere, sadly, because this is pretty high on the northern sky. To spot these, you're essentially going to want to just look anywhere but the Plough constellation, because they're going to be streaking away from there. So my advice, just grab a blanket, pop it on the floor, lie down and look directly up and enjoy the show. Now, one more thing, because I absolutely can't resist, because my favorite planet, Saturn, is pairing up with my favorite moon phase, a crescent moon, aka the Toenail moon, on the 14th of January in the early evening, just after sunset, before they set together a few hours later. If it's clear that night, make sure you try and spot this one, and also send me a picture on social media if you do, because let's face it, it's very likely to be cloudy here, because Saturn will actually be disappearing from our skies soon as it gets closer and closer to the sun from our perspective here on Earth. Actually swing around behind the sun and eventually reappear in the morning sky in late spring. All right, that's enough of looking up at the night sky. Let's come back down to Earth now and chat about what's been happening in space news in the past month. All right, there is a lot to get through this month, but let's start by looking at the latest color image released by NASA from JWST of the supernova remnant Cassiopeia A. This is an area of space where a star has run out of fuel and died by going supernova and then throwing off all of its outer layers of gas, which are now lit up by the core of the star left behind in the center. Now remember, this isn't a real color image because the James Webb Space Telescope detects infrared light and not visible light that we actually see in colors. But we do color the images because then your eye can pick up a lot of scientific details that it otherwise would miss in black and white. So the telescope takes an image which lets through shorter wavelengths of light given off by hotter regions, and those are colored blue, and then another that only lets through longer wavelengths of light given off by cooler regions, and those are colored red, and similarly with middle length wavelengths that are colored green in the middle. And so you can see where gas is hotter and cooler just by looking at this image. I mean, JWST's resolution is incredible, right? It can detect these tiny knots of gas here that are made of like sulfur, oxygen, argon, and neon that have all come from the star itself. And some of these filaments of debris here are too tiny even to be resolved by JWST, meaning that they're less than 10 billion miles across, just around about 100 times the distance from Earth to the sun. Now that suggests that this star, when it went supernova, essentially shattered like glass. So studying images like this gives us a really good idea of how this process happened, which was the scientific motivation for taking this data in the first place, which was written in this proposal, written by Millie Savljevic and collaborators. So I'm sure we're going to be seeing a paper analyzing this incredible image and all the other data they've collected published very soon. While we're on the topic of space telescopes, Hubble has been having issues with its gyroscopes once again this month. The gyroscopes are part of the system that allows the telescope to know which direction it's pointing in. So they're pretty crucial for the continued operation of this telescope if you want to look in a specific direction at a specific object. Now, over the 33 years that Hubble has been operational for, the gyroscopes have been replaced a number of times, but the last servicing mission now for Hubble was over 15 years ago, so we're stuck with the ones that we have now, since there's no space shuttle that can service it anymore. And now it just seems like every time there's trouble with Hubble, it's because of the gyroscopes, which isn't exactly surprising. It's always the moving parts in space that scupper you. So the telescope systems entered what's known as safe mode on the 19th of November when the problem was first identified, with one of the 3 gyros on board just giving some strange readings. So, for safety's sake, all the observations were stopped. Team at NASA thought they got everything back up and running again by the 21st of November and restarted observations, but then the telescope was back in safe mode by the 23rd of November. So the team spent a little bit longer analyzing all of the data from the gyros and have managed to get the telescope back up and running again on the 8th of December, and fingers crossed, everything seems to be fine. Fingers crossed, because, you know, I'd quite like to put in an application to use Hubble for my own science in the next round of proposals that are going to be due in spring that were just announced the other day. But it's likely that as Hubble continues to age, more issues like this are going to crop up, so we're going to have to get used to having some pauses in observations and some people just missing out on the observing time that they were scheduled to have, which is a real shame. But the hope is that Hubble will continue to operate well into the 2030s. Now, I want to chat a little bit about exoplanets now, because there's 3 studies that have come out related to exoplanets that I want to highlight. Starting with the beginning of planet formation in a dusty disk of gas around a newly formed star, which has been spotted for the first time around a star outside of our galaxy, the Milky Way, in the Large Magellanic Cloud, a dwarf galaxy in orbit around the Milky Way, which you can actually spot fairly easily as just like a fuzzy blob in southern hemisphere skies when you're away from light pollution. So this research was published by McLeod and collaborators, who used the Atacama Large Millimeter Array, or ALMA for short, which is an array of 66 radio telescopes in the desert in Chile to observe a massive young star. Similar to those that we see forming in the Milky Way, you know, these protostars that have these very thick, dusty gas disks around them that are really the beginning stages of planet formation around that very young star. The star they've observed actually has a jet of material being ejected from its poles as well, meaning it really is in the very active stages of still forming. Stuff really hasn't settled down yet. Now, the bigger the telescope, the smaller the thing is that you can actually see in the sky. And ALMA combines all of those individual dishes to make one big telescope that's effectively 16 kilometers wide. So it can see a lot of detail. And thanks to that resolution, they've been able to detect how the gas around the star is rotating. So by focusing on light given out a very specific wavelength from the molecule carbon monoxide, or CO, we can work out if that light has been Doppler shifted to longer or shorter wavelengths because it's moving either away or towards us at a certain speed. Just like with an ambulance, the siren sound wave gets squashed to a shorter wavelength as it comes towards you and then stretched out to a longer wavelength as it moves away from you. So here is that data for this star, with material coming towards us colored blue and material moving away from us colored red. And you can see how that rotation of gas has been picked out really nicely. So this is carbon and oxygen containing gas that's orbiting around a brand newly formed star that should eventually make some planets. So we're really seeing the very beginning stages of star and planet formation, and for the first time in a galaxy outside of the Milky Way. And what's really fun is that you can actually compare the properties of this massive young star to the ones that we see in the Milky Way, and you actually find they're similar in all aspects, except for the fact that in the Milky Way, they tend to be completely shrouded by dust, which blocks our view, so we can't really see what's going on, whereas here there's not really any dust at all. So that tells us a lot about the different sort of like formation conditions in the Milky Way and in the Large Magellanic Cloud. All right, so from very beginnings of planet formation stages to a perfectly formed system of 6 planets that's been discovered and published by Luque and collaborators. This was found in the TESS dataset, the Transiting Exoplanet Survey Satellite, a telescope which is in orbit around Earth and is monitoring the brightness of stars in the hope of detecting when a planet in orbit around them passes in front of the star, causing a dip in the star's brightness. This is known as the transit method of detecting exoplanets, because the exoplanet transits in front of its star. Now, the star they were looking at, HD 110067, is around about 80% of the size and mass of the Sun, and it's been monitored by TESS before, back in March to April of 2020. That data was processed by the telescope's data pipeline, and the algorithm flagged 2 possible planets based on the transits that it spotted, showing 4 dips in the brightness. Now, it was thought that 3 of those dips in brightness were caused by one planet, and that the 4th dip in brightness was caused by another planet in orbit around that star. But then TESS monitored HD 110067 again, this time between February and March 2022, and saw 9 dips in the brightness of the star, which could not be explained by a 2-planet model. Now, Luque and collaborators first of all noticed that some of the dips corresponded to the same planet, as they had the same shape and blocked the same amount of light. That confirmed there was at least 3 planets in the system. From that data, they could then start to make a model of the exoplanet system as they understood it then with 3 planets. You could work out how far away each planet is orbiting from its star and how long each orbit takes. And they noticed that the planets were actually in resonance with each other, a 3-to-2 resonance. So for every 3 orbits that planet B, furthest into the star, makes, planet C makes 2 orbits. And then for every 3 orbits that C makes, D makes 2 orbits. And they started to wonder, well, if there's more planets in this system, could you carry on this chain of resonance? So Luque and collaborators think the most likely explanation for their data is a 6-planet system in these resonances with each other. And I love that one of the best ways to represent this resonance is through sound. If you play a different note for each planet when it comes back to the same point in the orbit, you can really hear how all of them relate to each other as they go around this star. Now, as pretty sounding as that is, systems like this are also incredibly scientifically useful, because we think when planets first form around their stars, they start to drift all over the place as they interact with each other, migrating inwards or migrating outwards with all those interactions until they find a place that they're happy. In the solar system, for example, we don't think that any of the planets are, with their current positions, are anywhere near where they actually formed. So this system, HD 110067, to be in this perfect chain of resonance has to have formed that way from the beginning to be like that, which means that the positions they're in now are the positions that they were in when they formed. So we can study, how do the conditions that a planet formed in, like the environment it forms in, then affect, what size the planet is and what it's made out of. So when we look at the data of each of these transits here, we can actually work out an estimate for their sizes, for how much light they block. And it turns out that these 6 planets are all what we call sort of super Earths or sub-Neptunes, falling in that size gap from around about 2 to 3 times the radius of the Earth. But given their estimated masses, we think that means they're actually incredibly low density. So it's very likely they have very sort of thick gas atmospheres. They're much more like Neptune than a rocky planet like Earth. On top of that, HD 110067 is the brightest star to have been found hosting more than 4 transiting exoplanets. So although we found 7 and 8 planet systems before, they're around much smaller and cooler stars. Unlike HD 110067, which is much closer in size and mass and temperature to the sun. So it's actually very likely that the James Webb Space Telescope is now also going to observe these exoplanets and try to detect the light that passes through the planet's atmosphere when they transit in front of their star. And then in that light, we can then look for the fingerprints that are left behind by certain molecules to work out what their atmospheres are made of. And then again, be able to correlate that back to the environment in which these planets formed, because that hasn't changed since they formed. So a very exciting system, one that I think is going to get a lot of attention and be observed a lot in the next couple of years. Right, now the last exoplanet research paper I want to talk about is this one by Heller and Hipke, who've made us all very sad this month by saying it's unlikely that we've ever detected any exomoons, i.e. moons in orbit around planets in orbit around other stars. Now, there's only ever been 2 planets that anybody's ever claimed to have evidence of an exomoon in orbit around. The first was claimed in 2018 by Tichy, Kipping, and Schmidt. And then again, the same group claimed to have found another exomoon by surveying 70 exoplanets and looking for those extra dips in brightness that would be caused by the moon blocking light from the star as well as it trails the planet in its orbit. But now Heller and Hipke have reanalyzed that data and said that you can fit those transits just fine with just a planet-only model. And that the signal that the previous groups had claimed was the exomoon was actually just noise in the data, or maybe even just the star dimming weirdly on the edges, which is kind of sad. But sometimes that's just the way the data crumbles. But if we think about how prolific moons are in the solar system, right? There's over 200 known moons in orbit around Earth, Mars, Jupiter, Saturn, Uranus, and Neptune in total, then we figure there's got to be a plethora of exomoons out there just waiting to be discovered. I mean, the largest moon of the solar system is Ganymede, which is 40% of the size of Earth, and the smallest exoplanet known is Kepler-37b, which is 30% of the size of Earth. So we have the ability to do this. If there are moons out there that are as big as Jupiter's moon Ganymede, then we should be able to find them with our current instruments. It's just knowing where to look that's the problem. And finally, let's chat about the third highest energy cosmic ray particle to ever have hit the Earth's atmosphere since records began. Now, it hit back in May 2021, and after a lot of careful analysis, the research has now been published in November 2023 by Fujian collaborators from the Telescope Array Collaboration. Now, this cosmic ray event has been dubbed Amaterasu after the sun goddess in Japanese mythology, but it's highly unlikely that this event actually has anything to do with the sun. So this was detected by the Telescope Array, which is a cosmic ray detector in Utah in the USA, with 507 individual detectors of about 3 meters squared each, arranged in a grid separated by 1.2 kilometers. It gives the whole array a collecting area of 700 kilometers squared, which is continuously monitoring for these cosmic rays. Now, cosmic rays are single particles, so think like a single proton, so like the nucleus of a hydrogen atom, or the nucleus of a much heavier atom. And they're produced, we think, in things like supernovae, or in the material swirling around a growing black hole. And that travels across the universe before it happens to impact with another molecule at the top of the Earth's atmosphere. And the energy in that collision goes into creating a huge shower of other particles, which is what's then detected on the ground by these detectors. This is just like what happens in a particle accelerator that particle physicists build here on Earth, like in the LHC at CERN. Particles are accelerated to huge speeds, collided together, and then we observe the particles that are created in the high energy of the collision. Now, us physicists tend to think of the energy generated in these big particle colliders that particle physicists build as being pretty big, right? The maximum that we've achieved is around about 7 tera electron volts. But the Amaterasu particle had an energy 40 million times higher than that at 244 exa-electron volts. It's just huge. I mean, the reason we use electron volts usually for the energies of just these single subatomic particles is because they are so much smaller than the everyday energies that we're used to dealing with. But 244 exa-electron volts is 39 joules. So if you've got a 40-watt light bulb, then that's 40 joules of energy per second that it's using to stay lit. So one tiny particle hit the top of the Earth's atmosphere with the same energy that an entire light bulb uses in the space of a second. I've also seen someone calculate it as the same energy of a brick dropped from waist height to the ground. That kind of concentration of energy in one single particle is absolutely incredible. And yet it's still not the highest energy cosmic ray particle that we've ever detected. In 2001, a 280 exa-electron volt cosmic ray was detected. And in 1991, there was a 320 exa-electron volt cosmic ray detected, dubbed the oh my god particle because it was so energetic. That makes the Amaterasu particle the third highest energy cosmic ray we have ever detected, at 813 billion times more energetic than a typical cosmic ray that you would detect. Question is, what caused it? Well, here you can see which detectors in the telescope array actually registered the particles from this shower of particles that was generated when the cosmic ray hit the top of the atmosphere. And the color here corresponds to the time that the detections were made, with just microseconds separating the signals on the different detectors. It's really clear if you plot the data like this, showing what the signals look like at each detector against the time that they were detected on the x-axis. Now, from this delay and when all the signals arrived, you can use it to sort of triangulate back again to work out the direction in the sky that the particle has come from. Obviously, it's not perfect because as soon as the particle hits, the shower then spreads out over a wide area, but it gives you a rough idea and at least allows you to narrow it down to about half of the sky, at least. That's what this diagram shows here. This is the whole sky mapped out and flattened onto the page. That's why it's sort of like egg-shaped, because you've taken like the inside of a sphere and then like flattened it out onto a page. But the black solid circle here is the region which the Amaterasu particle could have come from. So I'm sure you'll agree it's pretty huge. Now you can look within that region for known objects that give out very high energy radiation, high energy particles. Things like supernova or galaxies with supermassive black holes in the center that are growing and taking in material. The kinds of things that we know can accelerate these particles up to the huge speeds and therefore the huge energies that we are detecting them with. But there's a lot of these known objects in that big circle region that the event could have come from. Plus, you also have to remember that these cosmic rays are charged particles. You know, if they're a proton or the nuclei of an atom, then they're going to be positively charged, which means as they travel towards us here on Earth, they've got to come through our galaxy, the Milky Way, which has a lot of magnetic fields which could deflect them. And then again, you think they've come from one direction, but actually they've been deflected and they've come from over there, which messes up, when you're trying to work out what could be the source of these cosmic rays. Now, depending on how big the nuclei of the atom actually is, the heavier the atom, then the more charged your nucleus is going to be. So technically the more it'll be deflected, but then also it'll be heavier, so it'll resist deflection slightly. So we can actually model for if you have a different size charged particle, how much is it going to get deflected from these different region. So that's what the collaboration have plotted here. In red is shown where the particle would have come from if it was a single photon. Then in purple is where the particle would have come from if it was a carbon atom nucleus. And then green is silicon and blue is iron. And so hopefully what you can see is that all of these models seem to take the origin of the Amaterasu particle to what's known as the local void, where there's just a dearth of nearby galaxies, just a big chunk of empty space. And while there are background galaxies in that region of sky that are a lot further away, they're thought to be too far away to give you a cosmic ray of the ultra high energies that we've observed here. Given the energy of the Amaterasu particle, the collaboration reckon it's somewhere between 10 and 27 megaparsecs away, which is around about 30 to 90 million light years away. So explaining the Amaterasu particle is gonna take some work, because either maybe, the Milky Way's magnetic field is stronger than we think. Perhaps there could be more deflection going on and therefore it would be coming from a different direction than we've realized. Or there is a source of high energy radiation in the local universe that we're just not aware of at all. Or, as the authors of this paper in the abstract so beautifully put it, we have an incomplete knowledge of particle physics. So there's clearly something going on here that we don't know about, which I think is a really exciting thought to take us into 2024. All right, that's it for Night Sky News for this month and for this year as well. Can you believe I've been making Night Sky News videos now for 5 years? So I just wanted to say I am so thankful to all of you who continue to tune into Night Sky News every single month and who share it with friends and with family. I'm so incredibly grateful. Don't worry, Night Sky News is not going anywhere. We are continuing into 2024. So as usual, if you see any space news stories on your travels around the internet that you want me to cover in a future Night Sky News video, then send them my way over on social media. All that's left for me to say is that I hope you all have a very Merry Christmas, or Happy Hanukkah if you celebrate, or if you don't, just a very restful betwixtmas and New Year period. But most importantly, until next time, everybody, happy stargazing. We have officially released? We've officially reached. We've not released the solstice. We have released the solstice into the world. International Space Station. I'm gonna get this eventually. Have some juice. Have some juice, that'll make things better. Oh, my juice has gone cold, that's sad. It's because the James Webb Space Telescope. People ask me why I say JWST rather than James Webb Space Telescope. And do you know what? It is just because every time I try and say it really quickly, I always stumble over it, and it's just easier to say JWST. That's the reason. It's very noisy motorbike outside. I forgot you existed. Ugh. I forgot that you existed. And I thought that it would kill me, but it didn't. And it seems like every time there's trouble with Hubble, that rhymes, trouble with Hubble at the minute. Reading, so for safety's sake, one of the 3 gyroscopes on broad, she's abroad. These big dusty disks of gas and dust. Compare their properties and their, what else would you compare except for their properties? Has to have formed that way. I probably should have done CA. Has to have formed that way. Whereas this single particle, this Amaterasu, Amaterasu. I'm Amaterasu. What generated the Amaterasu particle? No, Amaterasu. I'm a tiramisu. Wouldn't be a night Sky News if I didn't play with the jingle bell at some point, right? Whoa, I've knocked a bauble off, no! Nobody saw, la 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 la. Some won't know, it's fine. It's totally fine. In my heart is a cosmic ray particle, where it's super high energies and it creates a shower of lights. It's not really a shower of lights, is it? It's a shower of particles, but it sounds prettier this way.